Hi everyone, I'm Eddie Jones from the University of Bristol, and I'm going to be presenting Cyclic, a new proof system and automated reasoning tool combining cyclic and equational reasoning. And this is joint work with Luke Hong and Stephen Ramsey. So the starting point for this work is the desire to automatically reason about the behavior of functional programs. And we're in good stead to do so because these programs are typically pure and therefore referentially transparent, which means they admit these nice terse equational specifications, such as this map fusion law, which are great from the user's point of view because they don't require any external reasoning apparatus like separation logic. It's just the syntax of the program, so they're very easy to understand. So we're going to be dealing with equations, and these equations are going to be about algebraic data types, so we're going to need some mechanism for doing induction, which is a bit of a problem because induction is notoriously difficult to automate. So in part, this is because it's incomplete, which is not so much of an issue. We're used to dealing with incompleteness in program verification, but it's also non-analytic, which means that we can't proceed by analyzing the goal alone. We're going to need to bring in some insight about the problem domain. And this usually comes in the form of requiring auxiliary lemmas or strengthening the induction hypothesis in some way. It's worth noting that many tools have made great progress in this area through generalization or more recently theory exploration. But when we're considering mutually inductive structures, the situation is even harder because not only may our original induction hypothesis be insufficiently strong, but we need a complementary induction hypothesis about the other structures. And this is going to have to be entirely synthesized and maybe seemingly unrelated to the first. So currently, many tools just don't support mutual induction at all. And as mutually inductively defined structures are quite common in functional programming, we really wanted a tool that could handle them seamlessly. So we focused on designing an efficient basis that would support this kind of reasoning without worrying about lemma discovery and the other issues in this domain. So that's where cyclic proofs come in. So cyclic proofs are an alternative to traditional proof by induction that have grown in popularity in recent years because of their nice theoretical properties, which also lend themselves to great possible applications. So they replace a finite proof tree with an induction rule by a proof graph. So this can now have cycles, and the cycles are stand-in for induction hypotheses. So here we have a proof of the commutativity of addition. And it's represented as a proof tree here, but it's to be understood as a proof graph. So that's why there are some nodes which are labeled, in particular the root. And we can see on the top right-hand corner where we reference this root node 1, that's a cycle in the underlying proof graph. So instead of proceeding by induction, we just have case analysis. And in the interesting case, in the case of the successor in this right-hand branch, we do a bit of equational reasoning. We make use of this lemma. But ultimately, we end up at an instance of the original goal. It's add x prime y equals add yx prime, where x prime is the predecessor of x in this case. And because it's an instance of the previous goal, we can cycle back around discharging this, this goal using our original. Now, of course, not all such self-referential proofs are going to make sense as valid arguments. We could have trivially self-referential proofs. And so in addition to a local correctness that we're used to at all inference rules in the tree are well formed, we also need a global correctness condition. I won't go into the details of this too much, but informally it says that every infinite path has an infinitely decreasing trace, which is just a sequence of variables whose values are going to be decreasing for the context of that path. So what this means is that when we have an invalid judgment in our tree, we're going to get an infinitely decreasing sequence of values, which is obviously absurd in our inductive setting. Okay, so what's so good about cyclic proofs? Well, we don't need a fixed induction hypothesis or indeed an induction schema up front. We can just proceed by case analysis until we notice cycles and then discharge our hypotheses then. And this is like finding the induction hypothesis on the fly. So it's very well suited for goal-orientated reasoning because it's much more exploratory. And in particular, it's great for mutual induction because the other complementary induction hypothesis, we don't need to pick that up front either. We can just discover what is required about that complementary structure when we encounter that goal. So as a reference point for talking about our contribution, we're going to use Cyclist, which is a generic cyclic theorem prover. It's generic in the sense that it takes a user-defined set of inference rules and just does cyclic proofs search using these rules. So it's been very successful in applications with first-order logic and separation logic, and in particular, it can handle mutual induction seamlessly in these contexts, but it's known to have difficulty with equational reasoning. So the reason for this, at least at first, seems to be that equational reasoning is just has a load of non-determinism and redundancy with the usual rules like reflexivity and transitivity, which makes proof search intractable. However, for the most part, this complexity can be mitigated, especially in our setting where we're talking about functional programs which have like a confluent rewrite system underneath them, so we can just normalize stuff and not have to worry about symmetry. There's a directionality to it. So we can eliminate this complexity up until the point where we have to form cycles. And so what we thought, instead of forming cycles in a simple way after doing the equational reasoning, perhaps we could cram the equational reasoning into the way that we formed cycles. But unfortunately, this is not supported in the way that cyclists form cycles. So in cyclists, they have a matching function, which is also generic. It's applied by the user. And this says when one node logically subsumes another. So in the case of first-order logic, this is through instantiation or weakening and these kind of rules. And in separation logic, we also can use the frame rule. But if we're going to be doing equational reasoning at this point, in particular, if we want to use transitivity, we're not going to completely discharge the goal. We're going to simplify it using our induction hypothesis, which is just another node in the graph. We're going to simplify the goal, but not completely discharge it, because there will be two premises introduced by transitivity. So what we want to be able to do, equational reasoning at the point of forming cycles, doesn't fit into this matching function framework. So in Cyclic, we do something different. We manage cycles through the subst rule. So this is the subst rule, and on the face of it, in the logical interpretation, it's nothing novel. We're just replacing equals for equals in some context. But it's algorithmic application, which is novel and our main contribution. So normally in a goal-orientated setting, we're taking the conclusion of a premise as input, the goal, and we're discharging the premises as new goals, which need to be solved later. But we cannot do this with the subst rule because that requires synthesizing this M prime, which doesn't appear in our goal. So it seems that we can't do this in a goal-orientated setting, at least not in a tractable way. But in a cyclic setting, we can do something a bit different. We can take existing nodes in the graph and use them as lemmas. So we identify where some other node has one side of the equation matches a subterm of our goal, and we use that node to rewrite the goal. So we're using that as the lemma, and typically this is most useful when it's going to be our induction hypothesis, such as an ancestral node in the graph. But what's different about subs compared to other matching functions is that we're simplifying the goal, but we're not completely discharging it. We're going to have a continuation, which will then require further reasoning. And in particular, this could have further inductive reasoning. There could be cycles in that portion of the graph. So the subst rule is only used when forming cycles, and it's the only way in which cycles are formed in our cyclic proof system. So we found that in many proofs, this is essential and can replace what would otherwise require external lemmas. And so it's unsurprising in some sense that this subst rule is key to doing efficient proof search, because recent work has discovered many efficient model checking algorithms are also cyclic proof searches with an additional cut rule. So they've added these cut rules in, and that makes the algorithm much more efficient. And our subst rule is a specialized sort of cut rule for an equational setting. Okay, so we implemented CycleQ as a Haskell plugin for GHC, and so the users take their normal Haskell program and they annotate it with equations at the top level, and at compile time, CycleQ will attempt to construct cyclic proofs of these, and if so required, this will output a graphical format which is human readable. Here's an example of the proof of commutativity of addition, and we can see in the successor case, whereas before we required an external lemma before cycling, now we can cycle using this subst rule where the original root node is used as the lemma itself, and then this allows us to complete the proof without requiring external lemmas. Okay, so we ran our tool on a standard set of benchmark problems, and it solved over half of them in under 1/10 of a second, so it's very performant, especially compared to other tools in this domain. We also tested it on a small number of mutual induction problems because the benchmark suite didn't have any of these, because most tools can't do mutual induction. So it didn't have any problems with these handcrafted mutual induction problems, and again, most other tools would really struggle with these. It's worth noting, however, that there were most tools could handle more problems than Cyclic, and this is to be expected because Cyclic is really the core of a proof system that we later plan to add new features to. So there's a couple of things which are missing: conditional equations and lemma discovery, and many of the problems require these two features. There's no reason why these couldn't be added to a cyclic proof system, but we chose to focus in on the substrule to verify its validity in a minimal setting without orthogonal concerns. In the paper, we also showed that this technique subsumes an old technique, rewriting induction, which was also designed to handle mutual induction seamlessly, but has various other issues. And we do a slightly different way of verifying the global correctness condition from cyclist. We use these signs change graphs, which come from program termination work, and we found that their incremental nature allows us to check that these proofs are valid efficiently. Thanks for listening.
Okay, maybe I can take a chance to start with the first question. So can you tell us more about your, so the CycleQ is a proof system, right? So in your experiments, how does your algorithm exactly work? How does it search for proof?
So it takes the goal equation, and there's some stuff which it will do eagerly, like reducing the terms, and then it will pick a variable to do case analysis on. So we're building this kind of potentially infinite tree of case analyses with some simplification. But at some point, we're obviously going to have to do something different because this is an infinite tree. So we're constantly looking for other nodes in the graph which can be used to simplify the goal. And this is where we would form cycles.
Do you have any heuristics for which part of the tree to explore?
No, so currently it just takes all possible options other than the node itself, which would obviously create like an infinitely self-referential proof in a trivial way. But there is some possible simplifications. So you could just look at ancestors, which may be cheaper to do because there's less possible lemmas, but constrains the space of proofs in some way.
I see. And you mentioned that it lacks support for lemma discovery. Is that something can be done by just plugging existing techniques to your system? Okay.
Yeah, so there's no reason why you couldn't use existing techniques. And at the moment, the tool allows you to supply your own lemmas manually, and we found that this is sufficient for getting around that problem.
Nice.
Can you talk about the quantifier structure of your example with the commutativity of addition? Because if you look at the root of the tree at the bottom, we have like these fixed variables x and y, which based on the way you're using them in the proof, I'm understanding that they're implicitly universally quantified somehow because you're allowed to plug in x prime for x. So can you talk about how that works in general?
Yeah, so each node, all the variables are universally quantified, so there's no quantifier alternation, and we don't have any existential variables, so we can just instantiate any particular instance we like.
So at the beginning, you talked about properties, like you had an example with map and application. So is this trying to prove goal or lemmas of that sort, or trying to use lemmas of that sort?
Well, both, I guess. So like we're trying to prove those, but typically we're also going to need to use them at some point.
Maybe I can ask one more question. So it sounds like the mutual recursion causes a lot of troubles in existing systems. So can you give us more insights? What makes mutual recursion so bad?
So if we have our desired goal and it's got some mutually recursive structures involved, and we want to, even if we just pick this to be the induction hypothesis, we need a property about the other structure, and we can't just use this property because this property. So if we had like a rows tree, we've got some property about rows trees. We need a property about lists. It might just so happen that we know enough about lists through auxiliary lemmas, but you might not, and you can't always rely on auxiliary lemmas. So you need this other induction hypothesis. And you've got to synthesize that in some way, but that's a really complex task because you're quantifying over all possible formulas, which is the reason why it's non-analytic. So some tools just don't support this at all.
So is that fair to say the fundamental challenge is still about the induction hypothesis?
What was that, sorry?
the fundamental challenge is still about the induction hypothesis.
Yeah. Like picking the induction hypothesis is already hard. Picking two induction hypotheses about a structure which might not even be in scope is virtually impossible.
All right.
Cool.
Okay, let's thank Eddie again.